Hello everyone, my name is Etienne Wijler. I am a postdoc at Maastricht University and I'm here today to talk about the high-dimensional estimation of spatio-temporal models. The work that I will present is joint work with my co-author Hanno Reuvers, who is an assistant professor at Erasmus University in Rotterdam. So spatio-temporal models are very useful. Among other things, they can be used to model air pollutants in the air over time, or for example, to track the spread of COVID-19. The class of spatio-temporal models that I will look at is the following, where we assume that we have n observations of n different locations observed at time t, and we are going to allow for spatial dependence via this contemporaneous value of yt on the right-hand side and the spatial weight matrix A. And we allow for temporal dependence by also inserting a lagged level of yt. And the dynamics are regulated by the matrix B. Clearly, for the matrix A, we will need to assume that the diagonal is equal to 0. The question becomes, how can we estimate the unknown elements in A and B? Recent contributions in the literature show that a feasible way to estimate the elements in A and B is by the use of generalized YULE-WALKER estimation. What does that mean? Well, if we post-multiply our system by yt minus 1 prime and we take expectations, then we end up with the so-called YULE-WALKER equations over here. If we now have estimates for these population covariance matrices, then we have a feasible way to estimate A and B. So in other words, all that we need to do now is to plug in the sample counterparts of these population covariance matrices. And in principle, we are good to go, except there is one further issue, namely that every equation that we have here will give us n observations, but 2n minus 1 unknowns. So clearly, we need to impose some further structure to reduce the number of elements to estimate. Now, Gao et al. In 2019 proposed to assume that the matrices A and B are banded with bandwidth K0. And as long as K0 is small enough, we would be able to identify and estimate these elements in A and B. To be precise, if we look at the ith component of the YULE-WALKER equations, if A and B are banded, there are many zeros in here that we can remove. So let Ci denote the stacked AI and BI with the zeros removed. And correspondingly, we can remove then the irrelevant columns from sigma 1, sigma 0 and group those in VI. So then we end up with a much smaller system to estimate. And we could, for example, try to minimize the sum of squared residuals here, which is exactly what Gao et al. Proposed. So you kind of do an equation by equation estimation with regular OLS after you have obtained the YULE-WALKER equations. So this is nice, this works, but there is a major disadvantage. The motivation that we came up with that started this work is the following. So if we assume that we have a grid of spatial observations, we have 25 spatial units over here. If these spatial units are allowed to interact with their first order horizontal and vertical neighbor, if we then stack these observations row-wise and we convert it to our spatial VAR model from before, it turns out that the spatial weight matrix takes on the following form. So clearly there are many, many zeros and the matrix is indeed banded. We will see that these green diagonals, they actually model the horizontal interaction, whereas the red diagonals model the vertical interaction. But what we also see is that even though this matrix is banded, within the bandwidth, there is a lot of sparsity as well. And if we estimate this by OLS, we ignore all of this sparsity and we may lose efficiency as a result. So what we propose instead is to proceed with these YULE-WALKER equations, but estimate them sparsely by penalized regression. So one option would be to estimate the YULE-WALKER equations with the LASSO or the adaptive LASSO. The notation is almost the same as before, it's explained over here. So this is the regular sum of squares, but we simply add either an L1 penalty or a weighted L1 penalty. However, this would estimate this matrix sparsely, but it wouldn't really take into account this diagonal form of the sparsity. So another idea might be to actually not try to select or remove individual squares, individual coefficients, but actually to select or remove complete diagonals. And you may want to allow for zeros within the diagonal as well. For example, if we model the interaction between 5 and 6, there is no more horizontal interaction, which leads to these gaps over here. So a very suitable approach for this would be the sparse group lasso. The sparse group lasso cannot be estimated equation by equation like we did with the regular lasso, because this group penalty will impose cross-equation restrictions. So we have to stack the matrices, which is what we do over here. The notation is explained here. And we impose an L1 penalty on the individual elements and the group penalty on the diagonals. So some theoretical results. In order to derive theory, we will need to impose some assumptions. We will show these assumptions in detail at the end. You can pause the video and look at it in your own time. Summarizing, the assumptions that we need concern the stability of the system. So the reduced form VAR needs to exist and needs to be stable. For the innovations, we assume that they are a martingale difference sequence and geometrically strong mixing, and at least d greater or equal to 4 moments exist. For the design, the population covariance matrices in V, they need to satisfy a suitable compatibility condition, and they need to be bounded in L1 norm. Now we have a number of results. I think the easiest to show is the asymptotics for the lasso, and we have some finite sample results that we can show again as optional slides in the end. So for the asymptotics for the regular lasso, what we see is that if we impose restrictions on the relationship between the number of spatial units and the number of available time series observations t, and we impose that the penalty doesn't grow too fast, then we find that the prediction error over here, as well as the estimation error, basically converges to 0. For example, if n would be fixed, or if d would be very, very large, then you would see that the penalty is allowed to go to 0 almost at rate square root t, which implies that you actually have almost a square root t consistency that we know from the fixed dimensional case in L1 over here. For the adaptive lasso, we can go one step further, because we know that the adaptive lasso allows to also simultaneously obtain selection consistency. So if we put some extra assumptions on the penalty for the lasso and the adaptive lasso, again, they are shown at the end, then we can obtain the following two results, where we see that with probability converging to 1, the signs of our estimated coefficients correspond to the true signs. So that's a strong form of selection consistency. And the limit distribution of our adaptive lasso estimator corresponds to that of the so-called OLS oracle estimator. And the OLS oracle estimator is the estimator that basically uses the information a priori, which variables are the relevant ones. So that's kind of the best case scenario. For the sparse group lasso, we are still deriving some results. Estimation consistency we already have, but they are too preliminary to include in the slides. So let us look at some simulations to see in finite samples how does this perform. So we consider a 5 by 5 dimensional grid with spatial units, and the interactions are modeled by this matrix here, where every yellow square is a coefficient of 0.1 and the rest is 0. The temporal matrix B is a diagonal one with elements from a uniform distribution. And we are going to compare 4 different methods. So we have the banded OLS approach that we introduced in the beginning from Gao et al. Then we consider the plane lasso, a group lasso, as well as a penalized reduced VAR. So basically, under the correct stability assumptions, we can transform the system into a reduced form VAR without the spatial dependence and estimate that by the regular lasso. So that's the last estimator that we compare. So what we see is that over 1,000 different trials, if we take the average absolute coefficient, this is how the design looks like. We see that the OLS banded estimator does not impose any sparsity as to be expected. So you have these bandwidths here, these dense bandwidths. The LASSO does much better in terms of sparsity, although it doesn't really recognize fully the correct sparsity pattern. If we then look at the group LASSO, there we really start to see that the correct sparsity pattern is selected over all trials. So that's quite reassuring. In terms of the performance, when we look at the spatial weight matrix, we see that the banded OLS estimator does much, much worse compared to the sparse estimators. It's a sparse design, so it's what you expect, but the performance gain is obvious. For the temporal matrix, we find similar observations. And if we then, and this is quite interesting, if we look at what would happen if we consider the reduced form estimator, so we convert our estimates for A and B into the matrix that appears in the reduced form VAR, then we can also compare ourselves against the reduced form VAR estimator, as mentioned before, and we see that clearly the OLS banded estimator is still performing inferior. But the three penalized approaches do well, and the group LASSO approach actually still does better than the direct reduced form VAR estimator. So apparently the use of sparsity in the spatial model leads to some gains compared to the reduced form VAR estimator. Now, does this perform to empirical performance as well? Does this translate to empirical performance? We are going to consider an application in which we model the NO2 concentrations in the Netherlands based on 69 weather stations. We are going to fit a regular LASSO spatial VAR and a reduced form VAR based on the LASSO. We fit it to the first 80% of the data, hourly and daily data, and we will predict the remaining 20%. What we see is that the matrices A and B get estimated very sparsely. Only 3% is non-zero for the hourly data, for example, whereas 0.6% is non-zero for the daily data. The same for the temporal matrix. And WINS displays how often is the spatial VAR better at forecasting, for how many stations is it better in forecasting the NO2 concentration than the reduced form VAR. Turns out that for hourly data, this is in 86% the case, whereas for daily data, it's in 42%. And the significant gains are 77% for hourly and 36% for daily. So finally, some extensions that we are going to consider. Hopefully at some point we can allow exogenous variables in the system as well. We will look at different specialized penalty functions, such as the hierarchical LASSO. We're thinking to make an R package out of this. And furthermore, we will consider different kind of air pollutants in different cities based on satellite data. And we want to account for seasonality as well. So that was all I had to say. Thank you very much for listening. As promised, there will be a few optional slides now at the end for which you can pause the video. I look forward to seeing you in the live discussions. Thank you.